ladies and gentlemen, this class recording has started. So, starting off today, to get us rolling and to review what we did yesterday, I want you to do something for me. I want you to figure out for me how many hours are in 1 week. So, you have two choices. One, you can just do it real fast in your head, which is fine, or we can use the conversion factors that we were doing yesterday. I'm going to use the conversion factors here in a second, so if you want to practice that and then see how you did when I go and do it up here on the board, that might be a good idea too. All right? So, take a couple seconds, see if you can set up some conversion factors that show how many hours are in 1 week, and then we'll go through it together. Okay? Let's take a couple more seconds here. Okay, once again, just as a reminder, this problem is not about figuring out how many hours are in 1 week. I have complete faith that most of you could do that pretty easily. But I wanted to introduce the idea of the conversion factors, setting up a process so that later on today, when we are introduced to some topics that maybe we aren't as familiar with, we have a plan of attack of how to answer questions and how to attack the problem, even though we might not be familiar with the numbers. I think most of us probably real quick could figure out how many hours in a week by doing what? Multiplication. Specifically, you're going to multiply 24 times 7, because there's 7 days in a week and 24 hours in a day, and that would get you the number of hours in a week, okay? But let's go through with the conversion factors and make sure we understand the process, okay? So, first, what have I asked you to solve for here? Not a trick question, huh? Hours, right? So, right, how many hours means our answer should be in hours, because that's what I asked you to solve for, okay? Some information that we need that will help us solve this problem. What are some things that we know, either that were given to us in the problem, or that we just know that will help us out? Maya? How many hours in a day? So Maya, there are 24 hours in 1 day. What else? Sarah? How many days are in a week? There are 7 days in 1 week. Okay? And then there's one more thing that we need to show as a part of what we actually have to work with. What are we working with here? Remember, conversion factors don't change the measurement we've made. It just changes how we represent that measurement. How much time are we actually dealing with in this problem? How much time am I asking you about in this problem? What am I actually asking you about? I didn't ask you about 7 days. I asked you about... I didn't ask you how many hours were in 7 days. I asked you how many hours were in 1 week, right? This is the amount of time that we are dealing with, right? I'm not asking you for a different amount of time. It's still 1 week that we're concerned with, but how do we represent that 1 week? So we know that we have to go from 1 week and figure out how many hours there are. Our conversion factor, or our conversion problem, always starts with what measurement have we made that we are trying to change the way it's represented. So this problem will start off with 1 week. Okay? Then, conversion factor, right? We're multiplying. 2 things that we need to know about our conversion factor, or 2 things we talked about our conversion factor yesterday. What has to be true about our conversion factor? Julie, go ahead. It has to equal 1, right? Because we're not changing the amount of time, we're just changing how we represent it. So in essence, we are multiplying by 1. But in order for us to multiply by 1, what has to be true about the numerator and the denominator of our conversion factor? Tyler, go ahead. They have to be the same. So we have to make the top and the bottom of this conversion factor, in essence, the same thing. Okay? All right, but how do we do that? First, start with units. Okay? We want to get rid of this unit that is labeled week. So in our conversion factor, week has to show up, but where does week have to show up in our conversion factor? In the bottom, right? So weeks, week will show up here, okay? We don't have an expression written out in the information that we're working with that tells us hours in a week. But we do know how many days there are in a week. So we can make the top of this conversion factor days. Start with the units. Then we have to fill in numbers to make the top and the bottom, or the numerator and the denominator, an equal amount of whatever we're dealing with. So what numbers do we have to put in to make the top and the bottom equal to one another? Sarah, go ahead. 7 days, 1 week. All right? Now, we can make this step mathematically. You don't have to show it to me every time. If you want, we can think of putting this over 1, if that makes it easier for you to see. Now we're multiplying fractions. We know we're going to multiply tops, and we know we're going to multiply bottoms. Okay? But mathematically, we can take care of stuff, right? Week up here, week down here. What can we do with those units? Huh? These are going to cancel. Okay? Maya, what unit are we left with? Days. Is that what we want our final answer to be in? No. So, if that's not what we want our final answer to be in, right, what do you think we have to do? Turn it into hours by using what? Another conversion factor, right? So, times, right? Fraction bar. We can put that in parentheses if we want to. That's kind of up to you how we represent it, but okay. All right. What do we know has to go on the bottom of that conversion factor? Let's go units first, Julia. Days have to go on the bottom, right? And then, what should we have on the top? Hours, because that's ultimately where we want to end up. Then, we got to fill numbers in, right? To make the numerator and the denominator, in essence, the same. So what's numbers going in on the top? Go ahead, Julie. There we go, right? 24 on the top, 1 on the bottom, right? Mathematically, units, right? Days up here, days down there, day, day, right? I know one says day, the other one says days. Sorry, it's just what I wrote, okay? What's the only unit that we have left now in our entire problem? Hours, which is good, because that's what we want our answer to be in, right? I think we probably could see here, along the bottom, along the denominators of all these, we have 1, and 1, and 1, so the bottom's just going to be 1, right? And then the top, right, We have a 1 here, we have a 7 here, we have a 24. In essence, we're just multiplying what? 7 times 24, which is what we said before, right? And I think if I remember correctly, that should give us 168 hours. Is that correct? Okay. All right. Okay, go ahead. Mm-hmm. Technically, yeah. Although, I mean, okay, you're basically doing the same thing, yeah, right? But the reason I always start you with the units is because that's going to make sure that your numbers line up properly. The units have to cancel what we're trying to get rid of and leave us with what we're trying to go to. So that's when we get into the conversion factors today, we're going to do that as well. We're going to use the units to figure out how do we go from this step to the next step. Because all of you are very familiar with the relationships between hours and days and weeks, but you're not going to be as familiar with the relationships that we're going to talk about today. So if you have a plan as far as, okay, what should I set up first, what should I set up second, that will give you a path to follow. Even though maybe the numbers don't make much sense, you at least can follow the process, and that will get you to where you need to go. Okay? All right, good there. Let's talk now about counting atoms. There is going to, so pull out your outline that I gave you yesterday that says counting atoms up at the top, please. There is going to come a time in the future where we need a way to figure out how many atoms of a certain element are in a sample of that element. If we have a test tube full of sulfur powder, how many atoms do we have in that test tube? If we have a lump of charcoal, that is in essence carbon, how many atoms of carbon are in that lump of charcoal? We need a way to figure that out, so if we're talking about how they react with one another, we know how much of this and how much of that are actually coming together. But it's impractical for us to count them because they're just too small and there's just too many of them. So how do we do it? First, relative mass scale. We talked a little bit last week about relative scales. What do relative scales do for us? They compare. They don't necessarily measure, they just compare. And, right, in the bean counting lab, you set up a relative scale where you were comparing the size of beans to each other. But the first thing that you did was count out 100 of them, regardless of size. Remember last Friday, the first thing we talked about is you can't really compare a bag of plain M&Ms to a bag of peanut M&Ms because the sizes of each one are different. Even though they may weigh the same, we're not talking about the same kind or the same number of M&Ms. Relative scales will compare different things based on their size, so you can end up with the same number even though they may individually be different sizes. That's what you did in the bean counting lab. Using groups, it's easier to count stuff, especially if you have a lot of things that you need to count. For example, if you know that you're making a breakfast for a bunch of people and you need 3 dozen eggs, right? It's easier if they're already set up in groups of 12 to go 3 dozen, boom, 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 as opposed to counting 36 individual eggs. Or if you know, right, like maybe you're doing a big printing job for something, right, your invitations to a party, and maybe your party is so big that you need 3,000 invitations. It's a pretty big party, all right, but you know, whatever. If you know you need 3,000 of them, you could, in theory, count out 3,000 individual sheets of paper. But if you know that a package of paper is 500 sheets, you can count 6 packages as opposed to 3,000 individual sheets, right? Counting things in groups makes it easier to count them, right? So that will be to our advantage if we're talking about atoms, because atoms are small and hard to count. If we can group them somehow, that will make them easier to count. Atomic mass is a relative scale. We introduced it last week. Atoms are really small, duh, right? If we look at their actual masses, a proton has a mass of 1.67 times 10 to the minus 24th grams. So that's right. Yesterday, scientific notation, the minus powers, that means it's a very small number, right? It's these digits with 23 zeros in front of it. Really small. Using these numbers when we're talking about atoms, while we could compare them based on the number of protons and neutrons they have and what mass those protons and neutrons have, that gets to be, pretty cumbersome and kind of confusing and going to end up with some really, really small numbers, and there's lots of chances for mistakes there. Not to mention, we can't weigh this amount, right? So, if we can compare them to each other, even though they may be different sizes, we still can actually count them, at least relative to each other, okay? Atomic mass does that. Remember, atomic mass compares all atoms to the carbon-12 isotope. And carbon-12 gets assigned a value of exactly 12. So if an atom has a mass of 24, it is exactly twice as big as carbon-12. That doesn't tell you anything about its actual mass, it just tells you how it's related to carbon-12. If an atom has an atomic mass of 120, it's 10 times what carbon-12 is, right? I don't know how big that actually is grams-wise, but at least in comparison to other atoms, I know. And that's the relative scale part, okay? So how does that help us? On Friday, we talked about the idea that the red number on your periodic table is the average atomic mass. And the average atomic mass is a weighted average, taking into account all of the isotopes for that element and in what ratio they show up out there in nature. We talked about the idea that not every isotope of every element shows up as a 1-to-1-to-1 ratio. Some of them occur more frequently than others. We need to take that into account when calculating the average atomic mass, like we talked about on Friday. If you're taking, a mixture of the M&Ms, right? If the average tends towards a lower number, there's more plain M&Ms because they are smaller, right? And drags the average down. If the average tended towards a higher number, that would mean maybe there were more peanut M&Ms because peanut M&Ms are heavier, right? It would drag the average up, right? We have to take into account not only how much does each isotope weigh, but also how often does it show up. All right. Our relative scale for counting has been based off of the carbon-12 isotope, just like our relative scale for comparing the size of the atoms has been weighed or set up off of carbon-12. This is just like in the bean counting lab, where you went from the bottom of the front page to the top of the back page. You had all of the factors set up, right? Most of you Navy beans were in the middle, right? And then black beans were a little bit less than navy beans, and kidney beans were like 2.5 times what navy beans were, right? And you took that factor and multiplied it by the mass of 100 navy beans, because we were basing all of our counting off of the mass of the one in the middle. Okay? We base all of our counting of atoms off of carbon-12. And specifically, 12 grams of carbon-12. So if we took carbon-12 isotopes, put them on the balance until we reached exactly 12 grams, we would have a certain number of atoms. We could then use how big each isotope is relative to carbon-12 and figure out how much that standard number of atoms weighs because of how each individual atom compares, right? If kidney beans weigh 2.5 times navy beans, and we know how much 100 navy beans weighs, we just take that number and multiply it by 2.5, and that should tell us how much 100 kidney beans weigh, right? Just like you did in the lab, okay? All right, so what is that number? If we put carbon-12 atoms on the scale until we get to exactly 12.0, we would have this many atoms. 6.022 times 10 to the 23rd power. Okay? I never noticed that before about that box, so I meant to turn it so nobody would see it. So we refer to that number as Avogadro's number or Avogadro's constant. Okay? Avogadro did not figure out the number, it was named after him. So what does that mean? That means if we know that there are 6.022 times 10 to the 23rd carbon-12 atoms in 12 grams, because that's its atomic mass. If we know a certain isotope has a mass of 24, to get the same number of atoms, we would have to have 24 grams. Just like you did on the bean lab. We refer to the mass that gets us to this many atoms as the molar mass. Why is it called the molar mass? All right, good so far with this? Because that number of items, in this case that number of atoms, we refer to as a mole. The mole is an SI base unit for counting. It's always the same number of items. It just so happens that number is a very big number. 6.022 times 10 to the 23rd power. It is similar in a lot of ways to a dozen, in that it always represents the same number of things. For instance, Yesterday, we were using a dozen eggs, and eggs are a good example of something that is grouped by a dozen. But there's also something else out there that generally gets sold by the dozen, yes? Donuts, right? While they have different masses, a dozen eggs and a dozen donuts are both what? 12 of something. You can have a dozen anything as long as there are 12 of them. You can have a mole of anything as long as there are 6.022 times 10 to the 23rd power of them. Mole of donuts, not as easy, but it's the same idea, right? A mole of donuts would take you a long time to get through. Long time. So I don't care. I accept that challenge. One mole of donuts. Just so you know, like how big this number is, just for some perspective. I might be off a little bit on my, because I'm trying to remember now. But it takes the average person about a minute to count to 100. Okay? Average person, about a minute to count to 100. If you counted that fast, okay, 100 per minute, right? To get to this number would take you like 70 years. And that's not stopping like to like sleep or go to the bathroom or anything like that. It's like continuously. Like if you just counted for like 70 years, it would take you to get to that number. So, you know, that's the kind of number we're talking about here, right? And while it sounds delicious to eat that many donuts, it might be impractical. So, all right. Nothing. Impractical, yes. Impossible, no. So. All right. Where does that lead us? Okay. Because a mole represents a certain number of things, it can help us count. 1 mole of something is equal to 6.022 times 10 to the 23rd whatevers. In this case, those whatevers are atoms. Excuse me. I just get choked up when I talk about the mole. You guys will probably cry when talking about the mole too, but for different reasons. So. Whether you make the connection or not, we just talked about that if we put that many atoms on the scale, or a balance, I should say, we get a certain mass. That mass is called the molar mass. And we'll talk about that in just a second. The molar mass coming from the periodic table, specifically the average atomic mass, that number. And then, using sort of a math class idea, right? If A equals B and B equals C, what else has to be true? A equals C. So if 1 mole equals 6.022 times 10 to the 23rd atoms, and 6.022 times 10 to the 30 atoms equals the molar mass, then 1 mole of something has to equal the molar mass in grams for any element. Okay, good there for now, even if maybe we don't understand exactly what it means at this point in time. Okay. Open up your book, please, to page 133. Page 133. We're going to do a couple of sample calculations. It might be a good idea to do those sample calculations right at the bottom of the outline that we just finished filling out. There's lots of room down there. These examples go along with that outline, so it might be a good idea to do them there. Maybe another day. All right. On page 133, you'll see up at the top the heading says converting moles to grams. And then down at the bottom, there is this section here that says practice converting amount to mass. And that's what we're going to do today. So, it says, what is the mass in grams of each of the following? So anybody have a particular element that they'd like to work with today? Anybody got a real strong feeling, one or the other?
Yeah.
Well, let's pick one of the four that shows up in this chart right here. Okay, so let's go with sulfur, okay? So, for number one. All right, first thing we should do, right? First thing we should do when solving this problem or any problem is what? What's our first step? Fatima, go ahead. What are they asking for? So Fatima, what are they asking for in this problem? In? What is the mass in grams, right? So they want to know how many grams of sulfur are in this sample. Okay? After we've identified what we're looking for, now we start getting pieces of information together that will help us get there. What's one piece of information that they gave us to work with in this problem? Let's go obvious first, right? Well, how much sulfur do we have? Okay, so we know that we have 2.50 moles of sulfur. And Craig, we said that a mole represents a certain amount of atoms, right? 6.022 times 10 to the 23rd. So we can use that number to figure out how many atoms of sulfur we had if we wanted to. But that's not what this question asked us for, right? It asked us for grams. If you look at the outline we just finished, the very last part, we wrote down 3 equalities, 3 things that were equal to one another. And I believe the last one said 1 mole is equal to the molar mass in grams. Is that correct? That was the third one that we wrote down? Okay. All right. This is true for any element, but let's apply that to sulfur. So, 1 mole of sulfur is equal to the molar mass of sulfur. The molar mass is always a unit in grams. Earlier in the outline, I told you something about the molar mass. Numerically, it is equal to something that we talked about a couple days ago. Numerically, it is equal to the average atomic mass. So you go to your periodic table and you find sulfur. Julia, have you found sulfur on the periodic table yet? It's on the inside back cover, by the way. Other side.
Yes.
Atomic number? Atomic number? 16. Okay. Average atomic mass?
32.066.
Okay, 32.066. Your periodic tables might be a little bit different, just depending on how we rounded and stuff like that, okay? That number, 32.06, and you guys have 065, is that right? Okay. That number, Julia, you can write down 066, it's fine, okay? Because that's what your periodic table says, that's fine, okay? That number from the periodic table is what we refer to as the molar mass. If we were to have a sample that was 1 mole of sulfur, it would weigh this many grams. And then, Craig, we said that that also corresponds to how many atoms of sulfur. If we have 1 mole of something, it's 6.022 times 10 to the 23rd, right? And if we weighed out that many atoms, it would weigh this many grams, okay? Those are all equal, meaning we can use them in conversion factors, okay? All right, so let's go and do what they told us to do. A conversion problem starts with the number or the measurement or the unit that we're trying to get rid of, right? How much sulfur did they tell us we have in this problem? How much sulfur are we starting with? 2.50 moles. Remember, we're not changing the amount of sulfur, we're just representing it differently. So, conversion factor. First thing I had you do with the conversion factor was take care of what? Well, you were setting up conversion factors before. What did I make you do first or try to make you do first? Maya. Units. Maya, what unit has to go on the bottom of this conversion factor? Moles. Because we don't want this amount of sulfur to be measured in moles, specifically moles of sulfur, the S representing sulfur, right? So that's going to go on the bottom. Maya, what unit's going to go on the top of that conversion factor? Grams, because that's what they asked us to solve for. Do the units first. Now, we said what has to be true about the top and the bottom of our conversion factor? Sir, they have to be equal. So, Sarah, what numbers are we going to put in here to make them equal to one another, the top and the bottom? Bottom's going to be 1. Because that's how many grams are in 1 mole, right? So this will be 32.065. Okay? Run that through your calculator. No, did you run that through your calculator? What'd you get? 80.1625, and that's in grams. Okay? Last step. We are not changing how much sulfur we have, just how we represent it. Meaning, if our original measurement had 3 significant digits, which this one does, our answer should have 3 significant digits, so we should round this answer to 80.2. Okay? All right. Hold on. So, for tonight, homework. Some of it is just some questions about molar mass and moles and stuff like that. Some of it is a couple of samples. See how you do. We'll practice some more tomorrow.